Hello. In this video I will quickly comment on the method of solving questions like this when we have to classify stationary points of a given function. I will choose part 2 for my demo. So this is part 2 and this is a function in part 2 which we have to discuss. So the solution to such questions starts with the gradient. So first we compute the gradient, and that's what the gradient in this case. That's a vector. The first component of this vector is the x derivative of my function. The second component is the y derivative. And now we start looking for stationary points, and we look for them by solving this equation. Gradient equals 0 vector, which in component language is these two numerical equations with two unknowns. These two are relatively easy to solve. We just observe the second one implies that y equals negative x. We use this in the first one, and if we do so, we will end up having this quadratic equation which has two solutions, 0 and 1. And then we back substitute here, and we have 2 points where we need to check for local extremum behavior. So these are 2 stationary points which you have to analyze. After you identify these possible candidates for stationary points, the second step is the second derivative analysis based on Hessian metrics, and the Hessian for this function is that what it is? It's a matrix of size 2 by 2. First component is another x derivative on this one, so it's a double x derivative. This component is the y derivative on this expression, which is just 6. This one is the x derivative on this component, and this is the double y derivative. That's a Hessian matrix. Now, what we do, we spell out Hessian for... Actually, we compute the value of Hessian at every stationary point we found before. That's the Hessian at the point 0, 0. And it's convenient to factor out the common factor 6. This is a Hessian at the point 1, negative 1. And now we have to analyze both of these matrices and find out what's the combination of signs of the eigenvalues for these two matrices. Now when you do so, here's a little trick which I'm about to show you, which allows you to decide the combination of signs of eigenvalues without finding eigenvalues. Here's a trick. If you have a 2 by 2 matrix like this with random coefficients a, b, c, d, normally if you go and attempt to find the eigenvalues, what you have to do, you have to spell out the characteristic polynomial, which is this one. Now when you compute this polynomial, that's what you end up having. That's a computation of determinant of 2 by 2 matrix. A takes z times d takes c minus c times b. If you expand this and collect identical terms or similar terms, you will end up with this quadratic. And now the key fact I'd like to remind you right now is that when you have a quadratic, solutions to this quadratic equation, they satisfy the Vieta's theorem. And the Vieta's theorem says that the sum of the roots equal to the coefficient next to z with the opposite sign, and the product of the roots equal to the free term of your quadratic. And that's what I said. That's what I said here. This is the Vieta's theorem statement. This is a Vieta's theorem statement. Now, in the context of my matrix, it looks like that the sum of the roots equal to the value which is known as a trace of the matrix. Trace of the matrix is the sum of the diagonal elements, trace of the matrix A. And the product, you can easily identify in this expression the formula for the determinant of the matrix. Determinant of your matrix. So finally, I can summarize you this little trick. For 2 by 2 matrix, the sum of the roots, sum of the eigenvalues is the trace of that matrix, sum of the diagonal entries. And the product of the eigenvalues is the determinant of that matrix. If we use this trick here, for this matrix, for this Hessian, I can immediately say that the sum of the eigenvalues here will be the trace, which is 3 times 6, 18, and it's a positive value. And the product of the roots will be the determinant, which is, I made a typo here, it's supposed to say 6 squared actually, because the common factor in front of the matrix, when you compute the determinant, it will be factor to the power of the dimension of the matrix. But what we care about actually, not the numerical value of this determinant, but the signs. You see, we have two values which, when you add them, you end up having positive number. When you multiply them, you end up having positive number. These two pieces of information is enough to conclude that these two numbers are both positive, and hence you have a local mean. If you do similar analysis for this Hessian, the sum of the eigenvalues will be trace again, sum of diagonal entries, 6, and the product of the eigenvalues, it will be, again I need to fix this typo, it's supposed to be 6 squared, times -1, that's the determinant of this matrix, negative. Two numbers, such that when you add them, the result is positive, when you multiply them, the result is negative. It means that these two numbers of opposite signs, that's the only way to make sure that the product is negative. One factor must be positive, the other one must be negative. That's a saddle point condition. And that's the finish of the analysis. This little trick with the trace and determinant and this interplay with the signs, it helps a lot to make your analysis of the stationary points a lot quicker, because you don't need to find the actual numerical values for the eigenvalues.